everybody, welcome to Skype a Scientist Live. We're super glad that you're here today. Today we're going to be talking about space fireworks, which I'm so excited to hear more about with Tomas Ahumada. So, some housekeeping. Tomorrow we're going to be talking with Riley Black about science writing. So she's a science writer and has been for a long time, has written a number of books like My Friend the Brontosaurus and Skeleton Keys and others, and also had a long-running column in Scientific American. On Monday at 1 p.m. Eastern, we're going to be talking about hagfish slime, which I am so pumped about because hagfish are so weird and so fun. On the 16th, we're going to be talking about vocal learning and genetics in parrots. On the 19th at 1 p.m. Eastern, we're going to be talking about disaster drones. And then the following week is going to be cephalopod week. So we're going to be doing all squids all week, and cuttlefish and octopus. I'm just a bit partial to squid. And that's really all I have for you today. Of course, we shut down yesterday to talk all about racism in academia and STEM and what we can do to make it better for everybody. I hope you all had a good day doing that work as well. I know we've been giving you resources pretty much every day to look at there. Yeah, we hope you all got good work out of that day. With that, I am going to hand it over to Tomas.
Thank you. Well, I'm not sure how to begin. I was just going to say that I'm Tomas Ahumada. I'm from Chile. I'm doing a PhD in astronomy at the University of Maryland in College Park. College Park is a suburb of DC, so I live very close to the residential place, the presidential residence. I'm originally from Chile. I was born and raised in Santiago, and I moved to the US like 3.5 years ago. And since I got here, I've been working on trying to find space fireworks. And that's basically it, I guess. I've worked with, before in galaxies that eat, gas and dust and are very shiny. And I've also worked on supernovae. But I'm now trying to focus on trying to find those very weird fireworks.
Cool. So wait, did you just say that some galaxies will absorb gas and dust and that makes them shiny?
Very shiny, yes.
Oh my God. Can you tell us more about that?
Sure. So, well, astronomy, it's a science that compiles every other science. So this is very much of physics phenomenon. It happens when you have a black hole in the center of a galaxy, which is very, very heavy, and attracts a lot of matter. And it doesn't go straight into the black hole. So imagine this is the black hole. This is a particle of dust. It wouldn't go straight into the black hole. It will normally go around it and start orbiting as we do as the planet Earth. And because the black hole is so massive and so heavy, the velocity of this particle is pretty high. And when you have multiple particles doing the same, there's a lot of friction and everything is very energetic, and that produces light, basically. That is very energetic. And some of the galaxies have more dust than others, and that would, initiate the process of a shining galaxy. We call it active galactic nuclei, or quasars, and they have visible signatures you can look for in whatever telescope. So you point a star, you think it's a star. The name is quasi-stellar object because back in the 60s, they thought it was a star that was changing, the brightness, and it was not. It was actually a galaxy eating dust, which is, it's mind blowing. But you can look for those following certain criteria, basically, and that's what I tried to do.
Cool. So, okay, you have dust floating in space that's not incorporated with a galaxy. Did that dust fly off from some other galaxy? Like, how did it end up in the middle of nowhere?
Well,
Something.
it's galaxies are they start as a collection of dust. So you have to imagine at the very, very, very beginning, it's just a cloud of dust, and clumps within this cloud would start collapsing, and by collapsing, I mean gravity will start making it a place where things go to the center. So you have a kind of like a rock here, and then there's a dust particle here, and then they come together, and then like it starts growing and like attracts more and more, and it starts kind of like cleaning the like within the cloud. So you have this massive cloud and like little um in little locations within the cloud you start having that's how stars are born. And then if you have a lot, a galaxy is not, it's just a collection of stars.
Right.
But then you have places in between those two stars, for example, that they couldn't, here there's gas, star, gas, or dust. It's undistinguishable. So you have star, and then gas that wasn't collected by any of those. So it's not like it's just like randomly there. It was there before, but then you have stars that are like eating this gas, and then of course like in the center, as everything gravitates towards the center, in the very center you have a massive black hole, and that's what it's eating. And I say eating, but it doesn't have a digestive system. It's just like
Pulling things
collecting
together.
more and more particles.
Right. Cool. Awesome.
Yeah. And it took us like as humanity a long time to figure that out.
Totally.
Yeah.
I mean, yeah, it's wild that we even know that now. It's completely bananas. So Arjun has a question, and Arjun wants to know, how long does it take to make a black hole?
There are theories about it. We still don't really know, but it takes millions of years. There are also different sizes of black holes, so it really depends on which one you're asking. However, I think the easiest way to produce a black hole, quote unquote, because it's like the answer to that is you need a star, and like how can you get a star, right? So a star is again a collection of dust that just like it's collapsing, and you can, as it's collapsing, at some point it will like squeeze, and it will explode basically, and within the explosion, the remnant, it's normally a black hole. And sometimes are other kinds of stars, which are the ones that I'm trying to look for now. They're called neutron stars. It's where the gravity is so strong. So again, like everything's like being pushed. Everything's being pushed, and within the nuclei of the atom. So that's when you have to think very like a micro scale. So you have the proton, you have the electron around, but then the gravity is so strong that the electron and the proton come together. That's because of gravity. And then if you have two of these neutron stars and they collide, they produce more fireworks. But then and that's what I'm trying to look for, because that's really rare. It has been found only once in like effectively found. We have a few candidates that we think it is, but we haven't really found. So we're trying to use different methods to find it. But like answering the question, it takes millions of years for a star to evolve into a black hole, and then you can build a bigger one if you put one black hole here and another here, and then you merge them. Then you have like a bigger black hole now, and then and then you're like collecting black holes. But it takes billions of years.
Right. So cool. So the black hole, there's always a black hole in the center of galaxies. Is that true?
That is what we have found. Yes.
Okay, sounds good. And so is at the end of every star's life, it becomes a black hole?
Yes, but again, the one that is in the center of the galaxy doesn't necessarily come from the star's evolution. It comes from the very beginning. So you have the entire cloud, and here, like in the outskirts, you have stars being born very slowly, but the gravity in the center is very strong. So in the center is everything's happening faster,
Right.
and then the massive black hole is getting bigger faster than the stars are being created. So the origins of different black holes are also different.
Wild.
Yeah.
Awesome. So let's see. Ishan would like to know, can an asteroid be a space firework because it kind of looks like it when it comes through the atmosphere, or is that something different completely?
So what I call a firework, it's something that kind of shines and then disappears. And yes, asteroids are, I mean, they won't create a firework as you might think it is. Like, it's not like a New Year's Eve firework. But yes, whenever an asteroid comes through the atmosphere, it will shine. And depending on the size of the asteroid and I guess how bright it is during the day, if it happens at night, it's magnificent. But if it happens at noon, it's harder to see unless it's a very like big asteroid that is like being it's not exploding, but it's being burned basically by the atmosphere. It's very shiny.
Okay, so you're looking for events when two neutron stars collide?
Yes.
And then what happens?
So it happens that this was theorized because long ago, you have again two very massive objects that are composed only by neutrons. That it's a neutron doesn't want to be a neutron. The proton is positive, the electron is negative, and they don't want to be together. But you can put them together in a neutron, and if you have a lot of neutrons, you can create elements different than hydrogen or oxygen. You can go up to like creating gold. Like, do you know? Like, I guess we are all familiarized with gold. Where does it come from? Like, how did it go to Earth? Like, you can mine it. Yes, you can go to a mine and get gold, but then how did it how did it get to the mine? And we think it's when two neutron stars collide. So what happens is, again, you have a very massive object here, another here, and they start like, I call it a dance. They start dancing because they're both moving, and they start very far apart, and they over the years, over thousands of years, they start coming together, and at that point they merge, they collide, and that's when all these neutrons that you had come together. And since the center of gravity is changed, and it's not necessarily within one or the other, it's kind of like in the center, many of the neutrons are free now to go. So they're just like free to go, and they start making new elements. And most of the elements that are made in this process are radioactive. And radioactivity only means that they are shiny, and they're very energetic, and that's what produces the brightness, like a gloom.
Whoa.
It's like a bang, basically. It's like you have two things that collide, and then it explodes. It's I don't know, it's amazing.
That's awesome. So what we're seeing is radioactivity coming from. That's wild. Does it come in different colors?
They do. I mean, that's the other thing. When you study science, you realize how much we don't know and how much we cannot perceive. Like, if you think about it, elephants, for example, can hear things that we don't. that like dogs can hear things that we cannot. Bees can see in ultraviolet, and our like rainbow, like from red to violet, it's very limited. The colors they produce, and I call them color because it's like gamma rays.
Right.
It's another kind of light which is very energetic. They also produce X-rays. Like you may think, oh, what's the color of X-rays? Well, I cannot see an X-ray.
Right. Right.
But it's light. It's light that I cannot see. So they do produce different colors, and that's how we know, or that's how we can test whether the element produced is gold or is a hydrogen or oxygen or whatever, basically.
Whatever. Right. So is all the gold currently on Earth, was it made like in a star collision or something?
Well, that's what we think, yeah.
That's
I mean,
wild.
it is wild because like, if you go to the root of the problem, it's like, okay, hydrogen, the most basic element, it's just a proton with an electron going around. Then you got helium, which has 4 of this thingy, 2 protons and 2 neutrons. And then the oxygen has 8. And in order to have 8, you need to put 2 together and then put another one and put another one and that happens within a star.
Right.
But the star has a limit. It doesn't have enough gravity to put, gold has like 79. So how can we put 79 of these, all together? You need a massive explosion.
To happen. Yeah, you need an explosion.
Yeah. You need a massive explosion. Like, that's the only way. How can you energize something so much at a point that it's like just like energetic enough to hold basically all those 79 protons and neutrons?
Right. Cool. So one of our questions here is from Grant, age 10, and he says, what makes fireworks special enough to be studied, and why is it important for us to know about space fireworks? But is it just like, because that's how everything is made?
Basically, yeah.
Whoa. That's awesome.
It's basically how we know, but it's also to test our theories, because we think, gold is made in this process, but if we don't find it there, maybe we just have to look somewhere else.
Right.
But if we do find it, like, we can go and test another hypothesis, right? And I think that's like the process of science. Like, as long as you're trying to know more and more, and it's sometimes like I struggle with this. Like, is this meaningful to humanity? Like, do we really need to know where gold comes from?
Right.
But that's the beauty of science. You're learning stuff that you don't really know how are they going to impact the world at the end of the day.
Right. The things that have changed the world, like, we couldn't have predicted. Like, the person that was studying the jellyfish that discovered this thing called GFP, which is, for the audience, this is basically like a green protein that allows us to do all kinds of really cool stuff in cell biology to understand things down the line, for understanding how cancer works and all sorts of other stuff, and development works and all sorts of stuff. But we would, like, when that guy went to study a jellyfish, did he think he was going to change cell biology? No. So study whatever you want, because you never know what's going to come up,
And even like within this like pandemic, like I've seen studies on cows or llamas that I would never thought before. Like, why would you go to look for antibodies in a llama? Like it doesn't make any sense. But then it might make sense in the long run. Like, so, just enjoy whatever you do.
Enjoy whatever you enjoy. Go for it. You never know, you might save the world. It's so true. It's like a wild thing to say. It seems silly to say, but it's just the way it works, which is.
And one of my professors in Chile would explain, like, would put that into like a context on how hard it is to get funding, because you cannot predict what is going to happen. Like, you're trying to get more money to fund people that want to go farther, but you cannot promise anything because you don't know where it's going to impact. Is it in minery, or is it in the the healthcare, or is it on, I don't know, electricity, Wi-Fi,
Right.
or telecommunications? Who knows?
We don't know. Okay, yeah, that's very cool. So the next question is like, how do you look for these things? Like, are you sending satellites? Are you looking with telescopes? Like, how do you even find this stuff?
That's a good question, because I mean, we haven't yet find one.
Right.
But how do we know, first of all, if it exists? Um, so there are two main detectors, I want to say. Um, the first one is LIGO. LIGO is a gravitational wave observatory.
Uh-huh.
A gravitational wave is produced because these two, as we were talking about black holes at the beginning, black holes are very massive.
Mm-hmm.
And when they move around, they produce gravitational waves. In a galaxy, the movement is so slow. Like, you have a galaxy here. In the center, you have a black hole, and it's pretty much static. Like, it's not moving.
Right.
The only way to make something as like big as a massive black hole move is to have another massive black hole around, so they can attract each other. And that's what's happening within the Milky Way and Andromeda. Like, both galaxies are being attracted, but like the movement is so slow that we can barely detect it. We know it's happening because like physics works this way, but we cannot measure empirically how much it is. What we can do is go to the smaller kind of like part of the uh, black holes. And if you have a small black hole here and another here, and they are like orbiting each other, we can detect that with LIGO. And it happens the same with neutron stars. So neutron stars are very massive, and when they move, they produce gravitational waves, and we can detect those gravitational waves.
Gotcha.
That's one way to detect them. However, when they collide, they produce a gamma ray jet. So it's a lot of energy focused in like one point. It's like a laser, basically.
Ooh.
So it's like you have a laser, and it will turn on when they both collide. So collision, a very short pulse of this laser, and NASA has, well, NASA and like other space agencies have satellites on Earth that can detect these gamma rays.
Right.
So we have on one end LIGO, and on the other end, it's called Fermi. Fermi, the gamma ray detector satellite. So we can detect gravitational waves or gamma ray bursts.
Right. Cool.
And then we take telescopes on Earth and try to point whatever these two engines think they saw something.
Right. So like maybe so okay. First of all, how much time does it take for when these neutron stars start orbiting each other to when it's like, oh man, it's about to happen. Like we're about to get a collision.
So it takes like 10,000 years for them to be on this like dense. It's like kind of like an eternal dance. However, the very last the very few steps, very last steps, it's a minute and a half. And everything gets faster and faster, basically. So you have a very slow dance, but then when it gets closer, everything happens so fast. And then finally they collide in like a minute. And that's in that minute, it's what the window that we can see with the detectors we have.
So right now, do you have like candidate pairs that you're like waiting to maybe?
There are a few. They're actually, but those candidates are like going to collide in like 5,000 years. So
right. So you really have to pass it down to the next graduate student or whatever.
Yeah.
Eternally, right?
There are other sources. So you have neutron stars that are made of neutrons, but you have other kinds of stars that are produced by smaller stars exploding, white dwarfs, and they also can go again like in this dance and collide. And we have more of these that are expected to kind of like explode in like 10 to 20 years. And we're hopefully going to have more gravitational waves observatories, and like we already know where they are, so we don't really have to look for them.
Right.
But yeah.
Cool. Awesome. Rachel says, what's the most recent discovery we've learned about black holes? You were just watching Nova's Black Hole Apocalypse, but that information's 5 years old.
Yeah. The one I like to promote, it's I think you probably remember, there was like a picture of a black hole last year, and that picture. So again, if we start like from the beginning, you have a cloud full of dust, and in the center you have the black hole. So in order to take a picture, you need to go through the dust and see what is within that very dense region, and that's only achievable in a certain range, in a certain wavelength, with like radio telescopes, basically. And in order to see that very, very little, because it's like a very tiny, if you it's like the size of a star. It's like, can you try to point just one star in one galaxy, which is in the center? So it's like, and they had to use every basically every radio telescope on Earth at the same time, all together, to observe the center of the galaxy that they saw. And again, they didn't take a picture of the black hole, because you cannot see the black hole is black. What we saw is the material around shining.
Oh.
So it's basically, we saw the shadow of the black hole. But yeah, I think that's like the most amazing. But because it took so much effort, and like it's a leap like in the technology that we had at the time.
Right. So that you're talking about that picture that looks like an orange ring, and the
Yeah,
orange ring is like the stuff surrounding the actual black hole. Awesome.
And then because it's a ring, you can also test the general relativity, because general relativity says that you can bend space and time. So basically, the ring, if you think about Saturn, for example, Saturn, you only see the rings that are facing you, but you cannot see whatever is behind. But because the black hole has so much mass, the gravity effects bend whatever is behind and show it to you.
Whoa.
So you can see what's in front, but you can also see what's behind, because the mass of the black hole is bending the light from behind. So that's why, yeah, it's like
what? That's wild.
Yeah.
That's weird to think about, and I'm gonna have to think about that for a couple minutes later today. Just what just happened.
There are a bunch of YouTubers that would explain it by better than myself, and they also have like, you know, the equipment
Model
to
stuff,
visualize it.
Right. Very cool. So here's another question. Can black holes get smaller because they're constantly pulling things in, or do they get bigger?
So that's a good question. The size of a black hole, like how can we measure the size of a black hole? Okay, so as I like to picture it, like this is not reality, but like how I like to picture it is basically a marble that is so heavy that the light cannot escape basically from it. If the marble is this size, but it has enough mass to attract the light. So what happens is like we don't see it because the light cannot escape. So this is the light, comes here, but you trap it. So the size of the black hole depends on how massive it is, and it can vary. It doesn't shrink, it gets bigger, but it gets bigger because it's not like physically bigger. It's not like you're putting dust and like gluing it to the black hole. it's because you can hold light, stronger.
Right.
So it's not like how we know things get bigger, like putting atoms all together. No, it's not. It's just like you have more mass, so you can hold the light stronger.
Cool. Awesome. So do you look for where the light starts and you say anything in there is the black hole?
Yeah.
Gotcha. Okay. It's like a negative. Sounds good. Here's a question about stars broadly. When a star twinkles in the sky, what is making that happen? Like, what is making that twinkle appearance?
The twinkle comes from the atmosphere. So I like to imagine myself that I'm in a swimming pool of air. So if you change that and you imagine yourself in a swimming pool and you go to the very bottom and you're standing in the swimming pool, you're surrounded by water, and every movement of water, if you look at the sky within the water, you see how the water kind of moves and all the light is like deflected and everything is wobbly and that is the same in the atmosphere. So you're standing at the very bottom of a very big swimming pool of air, and the atmosphere is moving, right? And that movement, those winds or difference of pressure, would make stars twinkle. Because it's like having a pocket of air that is warmer and that makes the light move. It's called God, I forgot it, but it's not reflection. It's refraction.
Refraction. Okay, cool.
It's refraction.
Awesome, thank you. Gavin would like to know, do we know how long until Betelgeuse explodes?
Oh, that was kind of like a controversial discovery. So Betelgeuse is a star that it's in the constellation of Orion. It's very close. That's why we have a name for it. People in the ancient times, Greeks, named it because they could see it. What happened is that we normally monitor all the stars that are around, and people found that it was decreasing in brightness, and that could be a sign of that it's running out of gas or running out of energy. So it will it's getting close, tighter and tighter, and it cannot make it bigger. So there's no enough fuel to kind of counteract the gravity. So at some point it will collapse and it will explode. But the variation of its brightness can be also explained because of Betelgeuse is a huge star, and it's very complex, and it has it varies in brightness, and people have suggested that maybe the cycles of the star kind of got together and it made it dimmer. So we need to monitor farther to see if it's actually going to explode. My guess it's not, but it's we need to observe it for a longer time.
Sounds good. The next question, we've had a lot of questions about what happens if Earth goes into a black hole. What happens if a person goes into a black hole? Nothing good.
There was okay. I'm gonna. The thing what happens when you have a very massive object. If you think about it, if you have the Earth here and you jump, and then you go back to Earth because it's pulling you.
Right.
And the bigger the object, the bigger the pull. So there is actually an event. It's called tidal disruption event, and happens when you have a black hole and there's a star here, and when the star comes close to the black hole, the part that is closer to the black hole, in this case this one, is pulled stronger. The pull is stronger in this side than in this side, So the star kind of like squeeze, and it
Stretches out.
gets ripped. It gets ripped out, and it also produces a lot of light, and like people study that. But that's what would happen to Earth, for example, if it goes by a black hole or a person. That actually it's called when you're in astronomy 101. They teach you that as spaghettification, that you become an spaghetti, and
Oh,
like because your legs are going to be closer to the black hole, so the black hole pulls your legs harder than it pulls your head. So you just like you become a string. But just like this is hypothetical. Like we don't have a black hole nearby. There's no black hole that's going to eat us. And we know that because of the gravity that we have studied in our solar system. If we have a black hole, that means that it's very massive, and that means that it could, it will disrupt orbits, and we have knowledge about like how Jupiter works, and we have gone to not as humans, but we have sent satellites to Saturn, and the only way that we can do that is to make the calculations, and to make the calculations we need to know what's out there. So that's how we know that there's no black holes, so it wouldn't happen to Earth. However, if it would, hypothetically, someone creates a black hole out of something, we would get ripped, basically.
Get ripped? Lovely. Good to know. So you mentioned that the like collision that would happen between two neutron stars would take like a minute. So are those space fireworks also only visible for a minute, or do they like keep shimmering for longer?
It does keep it's shining for. So I was just reading a paper actually, and the only one that we have confirmed was in 2017.
Okay.
So it was like 3 years ago already, and it's still shining.
Cool.
And it happens that it's not because of the collision, it's also because the explosion. So you collide and then you explode, and many particles go like far apart, and they also interact with the gas that is around, and that is also producing more light. Yeah, so it's not just for a few minutes.
Cool. Arjun would like to know, can humans create a black hole? Like I remember when the Large Hadron Collider was like, they were about to do it, like start it up or whatever, we were worried about that. Like, is that a thing we could possibly even do?
Okay, to create a black hole, you need mass. Or a black hole that can actually, be. So there's another thing that can happen. Black holes can also shrink, but that's like
a whole new can of worms.
Even I don't understand how they shrink. But I don't think we can create a black hole because the conditions under a black hole can exist are so extreme that you cannot reproduce on Earth.
That's great news. Love to hear it.
Yeah.
Wonderful. Okay. So we've actually been talking about black holes for 40 minutes, and we try to keep these at 45. So I have a couple questions that I like to ask everybody at the end. First, is there anything that you wish I asked you about black holes today? Not black holes, neutron stars, space fireworks, the whole thing.
I think we covered everything. It's very complicated at some point, but I think we covered the basics.
Great. Okay. We've got two more questions. One, what do you wish everybody in the world knew about your area of expertise? And the second question is, what do you wish everybody in the world knew about literally anything?
Oh, good questions. I think the lesson in my research is that everything is connected, because we went from, as I explained before, we went from gravity, very massive objects, to the tiniest, thing, which is the atom. Like we're trying to explain how the gold atom is created. And for that, we're using the other extreme, which is the most massive stuff in the universe.
Mm-hmm.
And everything in between, you need to know. You need to connect dots, basically. You need to connect gravitational waves, gamma rays, X-rays, radio waves, blah, 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 in order to paint a whole picture.
Right.
Which I think it's important, just not, the lesson is like, okay, I don't really care if people understand where golds come from, but the thing is like, you cannot see a problem just from one end. There's a lot of things that affect that issue. And you need to be confident about the fact that you will never understand fully everything, but you will have a good understanding, enough understanding of a few things that will make you put things together.
Right. That's also a good lesson just for like society. Like everything is connected. That's a really broadly applicable lesson.
Yeah, and that's why like I like to promote research, but it's also not just because of research. It's because of like how it makes you understand the world, and it's very like you can see it. And the other question was,
what do you wish everybody knew related to literally anything? It can be as silly and insignificant or like big picture as you'd like.
I think we should, as humans, understand that we make mistakes, and then we can change our minds, and that's fine. Like if you thought at some point that something was right, but then you realize that it's not, you can move on, and you don't have to like hold to your thought because of your pride or because of what people say. I think the lesson for humanity is that like it's okay to be wrong. Just like own it and move on and like be a better human.
Beautiful advice. That's great. Perfect. What a good way to end this session. Okay, so where can we find you on social media or on the internet? And is there anything else you'd like to plug before we wrap up?
I have Instagram. If you have questions, you can Tomas
underscore
Ahumada. I have Twitter, but like I never use it. That's the thing. Like you can drop me an email. I don't know. Just Google my name. You'll find me, I guess.
That's good.
I'm not trying to become an influencer. So. Oh, we do have my native language is Spanish. So there is a site called Astrovitos, in which a bunch of us scientists from Latin America kind of like digest research and do it in Spanish. There are also resources for, like yesterday, we were trying to compile resources to fight racism in academia, and like there are a lot of anti-racist academics that are in Spanish for people that speak Spanish. So maybe that, I don't know.
That sounds great. Yeah,
feel free to contact me if you have questions.
Great. Okay. Well, thank you so much for being with us today. I really appreciate it. And thank you, Aaron, for signing for us. Tomorrow, we're going to be talking about science writing at 1. Monday, we're talking about hagfish slime. So get excited, and thank you for joining us and being curious, and we'll see you later.
Thank you, everyone.
Thanks. Bye.
Bye-bye.